By now, you've learned quite a lot about networks in one form or another, and in this program we'll be looking at a real network, and a very large one. We'll be looking at the network which transmits electricity to all parts of England and Wales, a network usually known as the national grid. The purpose of this network is to provide an economic and secure supply of power to all parts of the country. By secure, we mean a system that isn't prone to failure if, for example, there's a storm and a single line were to blow down. We'll be seeing how the CEGB operates this network to provide this secure transmission system, and how they use network theory in order to help them to make the day-to-day decisions in its operation. The network itself is controlled from here, the National Control Centre. And in the network, there are a great many components. First of all, there are the sources, the power stations. These may be coal-fired, like this one, or oil-fired, like this one. We have to remember that with the high cost of oil nowadays, it may be more expensive to run. And then there are the nuclear stations, like this one. These are most economically operated when they're running at full load, because most of their cost is in the course of construction. Then there are the transmission lines, the arcs of the network, that operate at a very high voltage, so that a relatively low current is needed to transmit a considerable amount of power, and it's power that's the commodity flowing in this network. And each of these supergrid lines is limited in the amount of power it can transmit by the heat that's generated in the line by the current flowing through it. In other words, it has a capacity. On a cold winter's day, the wind will blow a lot of this heat away, and we can pass more current down the line, and in fact, the capacity can be nearly double that of a hot summer's day. Now, the high voltages of the transmission lines aren't suitable for the users, and so they must be transformed down at substations like this one. First to 132,000 volts, and then to 33,000, and so on by several stages, until we reach the familiar 240 volts of the domestic supply. Finally, in the network, we have the sinks, the users. An industrial user, like this steelworks, can consume a considerable amount of power. The additional load on the grid can be quite considerable.
And then there's you and me, the domestic consumer, turning on or off our electrical equipment, like this television set at the end of a program. And we'll see later that the National Grid Controller also has a television program schedule in front of him to help him cope with the fluctuating demand at the beginning and end of programs. So, you have now seen how many different components there are in this system. This diagram, which we'll be looking at later in more detail, shows you something of the overall complexity. How can we use network theory in the successful operation of such a vast undertaking? To find the answer to that, we went to the CEGB National Control Centre at Bankside in London, and we talked to Eric Scheffner, the National Control Manager.
In order to use any theory, we have to make a model. And in the national grid, we've got a very complex system to make a model of. So the first question, Eric, is how do you get round this tremendous complexity and get a model that's simple enough to give you useful answers?
We couldn't possibly model the whole of the distribution system. There are too many cables and too much detail. So what we do is we select the major distribution lines that transmit large amounts of power around the country, and we make a model. In practice, this means the supergrid, that is the 275 kV and 400 kV systems. In the model, the substations are treated as sinks. The model, in fact, is the top layer of the grid system. When we study regional level, we take the results from the first layer of the model and add the detail of the regional systems, that is the 132 kV network, again representing the network as sinks, sources and arcs, and so on, adding the detail down the various levels until we get down to the consumer networks, studying smaller and smaller areas. Here at National Control, we're only concerned with the supergrid, that is the top layer of the grid system. In the model, the main sources are our power stations. The substations are treated as sinks, and the transmission lines as arcs of the network. Although we have simplified the network, it is still a complex network diagram, but it gives us useful results from a workable model.
Okay, to show you how the top layer model can give useful information, I've taken a very tiny corner of this type of model. It's tiny because I can then put some numbers on it and do some calculations that don't need a computer. And this will demonstrate the sort of information that the CEGB's computer will give for the whole of the top layer supergrid model. Now here we have three boxes, A, B, and C. Each represents a vertex in the network. A and C represent both power stations and substations, and so are both source and sink. B, on the other hand, is just a sink. Now the first thing I'm going to do is suggest that the cables connecting these have a maximum capacity of 2 gigawatts. That's all these lines can carry a maximum capacity of 2 gigawatts. Also, I'm going to suggest that there is a demand of 1 gigawatt at A, 10 gigawatts at B, and 1 gigawatt at C. In addition, the power station at A can supply at most 2 gigawatts, and so also the power station at C. However, C is an oil-fired station, and therefore it is rather expensive to run, so we don't want to use it if possible. So for some of the time, we will want to treat it as a sink. Now let's try and establish a pattern of flows on this network. We might begin by suggesting we have 2 gigawatts coming in on this line, 2 gigawatts on this line. Before I go on, you'll notice this symbol refers to the maximum capacity, the first number. The second number is the flow actually on the line. So this has a maximum of 2, a flow of 2. Now we've got a flow of 2 plus 2 is 4 gigawatts into A. We're generating 2 locally here, which makes 6 altogether. We have to supply a local demand of 1, so that leaves us with 5 that we can transmit on to B. How do we do this? One possible way is to have 2 gigawatts along this line, 2 along this line, and 1 along the third line, making 2, 4, 5 gigawatts into B. However, we have to supply a local demand at B of 10 gigawatts. How can we get the remaining 5 into B? The only way to do that is to draw some power from C. We have another 3 lines here. Let's adopt the same pattern. Let's take 2 gigawatts along this line, 2 along this line, and 1 along this line. So now we've satisfied the demand both at A and B. However, where's this coming from? This 5 gigawatts has to come from C. Suppose we don't use C, the generating capacity of C, because it's expensive. We've got 5 here, and we have to supply 1 locally. That means we somehow have to get 6 gigawatts into C from elsewhere. We can do that along the 4 available lines. One possible pattern would be the following. Would be to have 2 gigawatts on this line, 2 on this line, 1 on the third, and 1 on the fourth line. And as you can see, this satisfies all the demands without generating any power at C. The next question we would like to ask is what happens if one of the lines goes down for some reason? For example, of the 4 lines coming into C, suppose this one went down. Can we still satisfy the demands that we require? Well, we still require 6 gigawatts to pass through the C node. So how can we do this? We have 3 lines still available into C. They each have a maximum capacity of 2. So if we just step up these 2 lines to 2 gigawatt flows, we can do it. We'd have 2 plus 2 plus 2 is 6 gigawatts. We can still satisfy the demand. A problem arises, though, if the demand here is 3 gigawatts instead of 1. And then we're in trouble. And we cannot get, we need 8 because we've got 5 here and 3 locally. We would need 8 gigawatts. We cannot get that into C through 3 lines. We would therefore have to generate power locally at C, and also this would require plenty of warning and time to bring up the turbines to speed. Well, you can see the general idea. The same sort of arguments apply if this line here between A and B went down. However, suppose we look at the line into A, this line. this is a critical line. If this one went down, we are in trouble. We only have 2 gigawatts coming in on this line, 2 gigawatts generated locally, making 4, 1 for the local demand, which means we only have 3 left to pass on to B. We can do that by having 2 on one line and 1 on the other. As for example, we're now supplying 3 into B. We require 10. Where do we get the other 7? There's actually no way we can possibly get 7 gigawatts along these 3 lines because they have a maximum capacity of 2 each. We can only get 6 in. The system would not cope with that unless we brought on another power station in the area of B, which again would take lots of time to run up all the various equipment. Well, we don't want you to think of this example as being too realistic in every detail. Like every model, it's a broad brush picture, but it does give some idea of the sort of calculations that the computer will do with the CEGB top layer model and the sort of information it can give us.
This is a printout from the computer model. The model is fed with predicted data for the following day's demand and shows the likely bottlenecks, that is, lines that could be overloaded if a single line fails.
So in our terminology, you're looking for a potential saturated arc, that is, a line which would be at maximum capacity if a single line elsewhere were to fail.
That's right. In fact, we go one stage further and study the situation where 2 lines fail simultaneously, again looking for the situation where a line is approaching maximum capacity. The model assists us in defining the areas supported by these lines and in setting the power transfer capability into these areas. We then mark the network diagram with the boundary of these areas, and we also indicate on the diagram the power transfer capability into that area.
The boundary line round this area looks something like what we've been calling a cut. And we might think that this is an application of the max flow min cut theorem. But it isn't quite as simple as that for 2 reasons. First of all, for this cut, we have flows only in one direction, whereas for the cuts we've seen before, we've allowed flows in both directions. And secondly, we've looked in the unit, for the most part, at systems with one source and one sink. And here we've got power sources on both sides of the cut, so we can supplement the power flow into this area with generation inside it. So we can't use analytical methods to find an actual minimum cut. How then do the engineers find exactly where the cut should be drawn?
The model defines 2 points on the cut. First, it defines the circuits that are potentially overloaded, and second, it defines the circuits whose failure would cause the overload. The remainder of the cut is derived by engineering judgment being applied to the study outputs. Occasionally, there are different viewpoints on just where the limit boundary should be drawn.
You said that the model was fed with predicted data. What happens if the predictions turn out to be wrong? For example, if it's a fine day unexpectedly?
We use a second model which takes actual data direct from the power system. This data is transmitted to our regional control centres and is then sent on to our computers at national control. If you go into the control room, you can see the actual output of the model directly available to the control engineer.
And here, we're in the national control room, the nerve centre of the grid control system. And in the middle of the wall behind me, there's a diagram of the whole of the top layer of the national grid. Then over on this side, we have a map showing the 7 operating regions and how much power each region is producing and consuming. On the other side, there's a map that's showing the power transfers across each regional boundary and to and from the Electricity Board's neighbours, the South of Scotland Electricity Board and Électricité de France. Then over on this side, we have the switching engineer. It's his job to look after the setup of the switches at all the main substations. At the desk on the other side is the loading engineer, and it's his job to look after the loading, the amount of power produced at each power station. Then here in the middle is the man in the hot seat, the national control engineer. And it's his decisions that make sure you don't get a power cut. To help him make those decisions, he's got a lot of information available. For example, he's got the television schedules we referred to earlier, because at the end of a popular program, when you all get up and put your kettles on, that makes quite an extra bit of demand on the grid. And he's got a lot more information transmitted from remote instrumentation actually out on the network right into the computers here, which he can call up on a visual display unit like this one. We've called up here a picture of a particular substation, and by looking carefully at these symbols, the engineer can tell how the substation is configured, that is, which incoming lines are connected to which outgoing lines. And that brings us to a practical point. When part of this network gets near to saturation, the grid control engineer can do one of two things about it. He can either change the pattern of sources in the grid, that is, he can look at the power station outputs and ask at one station to increase its power output, and perhaps another station to decrease its power output, and there you can see the actual power station outputs we're getting at the moment. Alternatively, he can reconfigure the network. That is, he can change the arcs which join one vertex or substation to another one. And the switches at the substations will enable him to do this. But if he changes the configuration of the network, where then are the critical arcs, that is, the lines that are likely to become saturated in the event of a line failure? To get this information, he needs to find the results of the online network flow calculation. The online model takes its data direct from the remote instrumentation, and then, like the offline model, finds which lines would become saturated in the event of a line failure or in the event of two simultaneous line failures. Now, with all this information, the controller can see where in the network is likely to be critical, and he can plan appropriate remedial action if necessary. The online model can therefore be extremely useful to the national control engineers because it keeps him informed from hour to hour as to which parts of the network he needs to keep a close eye on. And because the data in the model is real, current information, and not just predictions, the information he's got is always literally up to the minute.
So let's look at the sort of information a control engineer could get from the online model and the sort of action he might have to take as a result. If we look at the southern end of the national grid, we can see that there are only 3 pairs of lines leading to the south coast. The first of these comes from Melksham down through Hinkley Point to the southwest region. Notice that Hinkley Point is a nuclear station and is therefore providing maximum power for most of the time. This means that most of these lines carry a fairly constant load. The second pair of lines comes from Bramley down through Fleet in the Southampton area. We shall have more to say about that in a moment. The third pair of lines comes from Kemsley down to Canterbury North in the southeast. Notice that Dungeness is also in the same area and that this is also a nuclear station, providing maximum power and constant load in these lines. So the critical line tends to be from Bramley to Fleet, where the amount of power flow can vary considerably with the demand all the way along the south coast. There's a lot of demand along here. Most of these square blocks represent both sources and sinks, and apart from the nuclear stations, the amount of sink is far greater than the amount of source. Of course, the other big power station in the south coast strip is at Fawley here, but that's oil-fired, and so it's expensive to run. During the night, Fawley is usually shut down. It's not economic to run it, with the price of oil at its present level. But what happens during the evening peak? Let's assume the online models predict that the Bramley Fleet line is getting near to saturation. If a line goes down, this would tend to overload both of the other north-south lines here and here, causing them to trip out. In other words, they would be taken out of service automatically to protect them from damage. If this did happen, the south of England would be separated from the rest of the country. There would be no north-south connection at all. This is potentially disastrous. The whole national grid would lose its integrity and flexibility, and the south coast could be blacked out completely. So the controller might do one of two things to remedy this. He might ask Fawley to keep producing for a longer period than normal, to provide more power within the southern area itself. Alternatively, he might reconfigure the network in the South Wales area and operate Melksham in such a way that more power was available to go down to Hinkley Point. thus relieving the pressure on the Bramley-Fleet lines. A further possibility, of course, is to bring on new generating capacity as the proposed solution in the case of a line failure. In this case, again, it must be anticipated some time in advance, because as we have said several times, the time needed to bring a boiler up to pressure and a turbine up to speed can be quite considerable.
So you see, there are a lot of other factors that must be built into operating the real system that make it altogether more complex than the simple network models we've been looking at in the units. But you'll have noticed throughout the program that theoretical ideas keep creeping in. For example, the models use Kirchhoff's laws in order to calculate the network flows. And we saw how the idea of a cut was useful in identifying difficult areas of the grid. So there are a lot of ways in which even the simplest parts of network theory can be of real help in operating a complex system like the national grid. And without this basic theory, it would be an impossibly difficult task to operate this system in the reliable, economic, and efficient way that we've come to take for granted.